Hello gang, today we're going to learn something new and exciting, solving systems of equations by graphing. So in the past we've learned how to draw a graph of a line, just using one line and solving one equation at a time. What solving systems does is it allows us to graph two lines separately and figure out where they intersect each other. This may be important when you're trying to compare growth rates or speeds of cars that start at different places and intersect at a path or things of that nature. So that's why we've been practicing equations of lines, because now we're going to need to make sure we incorporate two of them. If you don't get it in the first shot, don't panic. We are going to take our time and make sure we go through this slowly. All right, so solving systems, as I said, it's sometimes necessary to graph two lines at once. Here's an example: the tortoise and the hare. All right, you have your hare. Now the hare's graph in this case isn't one straight line, but it gives you the idea of why we would use it. So the hare, of course, is if this side here is distance and this is time. The hare obviously covers a lot more distance in a short amount of time. If we look at where they both are at this point, all right, maybe the hare went 3 yards to the turtle's less than 1 yard after 1 minute or after 1 second, something along those lines. So, but the hare, of course, gets distracted and doesn't move for a little bit, or does something else where he's not gaining any ground at a certain point, and the tortoise just stays steady. So this here, where they intersect, would be the point where the hare actually passes or where the tortoise actually passes the hare. So in this point represents a value. This value would be, remember, if we go xy, well, it's 6 over, and it's like, we'll call it 4.75 up. It's not quite 5, but it looks more than 4.5. So in this case, we're just going to estimate it at 4.75. So then what this tells us is that if this distance was in, we'll call it meters, and the time was in minutes, or something like that, then the hare, then they would cross paths after they traveled 6 meters or after they went 4.75 minutes. So that's the point where they cross paths. And we'll get more practice at this as we go along. I'm going to show you 2 more examples. This way we have a general understanding of what exactly we're doing. So initially you're just going to be given 2 equations like this. So y equals x plus 2, y equals 3x plus 1. Remember, it's easiest to keep them in this form. So if they're not both in this form and you have 2 equations of a line that you need to plot, it might be best to convert the equation so that it looks like this: y equals mx plus b. Because now we have a point, which is the y-intercept, and we have the slope, which is m. So in this graph here, they graphed each line. Y equals x plus 2 is the red one, y equals 3x minus 2 is the blue one, and they want to know where they intersect. Well, as you can see on this graph, they intersect at 2, 4. And then what they do is they have you do a quick check. So what this means is that 2, 4 should be a solution for both of these lines. If they both intersect at that point, that means they both existed at that point, which means this point here should be a solution to both lines. So if you plug 2, 4 back into the equations up here, they both should equal, which is what they do at the bottom part of the page. So 2 plus 2 is 4, 3 times 2 is 6, minus 2 is 4, They check out. So the solution of the system, or the point of intersection, is 2, 4. Here's one other example before we wrap up. This is a more practical example. So the scientists are studying the weights of 2 alligators over a period of time, and they're trying to establish some kind of growth rate. So they want to know, when did they weigh the same amount. Maybe they're giving them 2 different types of food to see how fast they grow, or maybe they have 2 different sets of parents and they want to see, which is the more ideal parent grouping, to see if they want to produce larger alligators or smaller ones, or however. Then they need to be able to track their weights and sizes. So here they set up 2 equations to track their weights. And they set up these equations by maybe plotting them for the first 3 months. This way they kind of know where the line is. So if we do the T-chart, we plot the first 3 months like we did earlier, you can then develop a trend line that should show you what that continued path would be on. So that's what they did here. They found that the alligator 1's weight, the equation of his line was 4 plus 1.5 T, and alligator 2 is 6 plus 1 T. So here are the equations. When you graph them on graph paper, they should look like this. Now, it's very, very important that when you're solving systems and you're trying to find an intersection point, that you are exact. So I would try doing this on grid paper on your computer, all right? Or if you have graphing paper, or print out maybe a grid, I will try and put one in the resources. That's a good template to print out, and then maybe use a ruler to draw these lines. So that's how you will get exact intersection points. So it's very important to be as precise as possible when doing this particular type of drawing and graph problem. Anyway, once they plot the points, they see that they intersected this point here, which, as you can see, is after 4 months, they both weigh 10 pounds. So that's where the lines intersect. Hopefully, just by practicing this more, we will get a better understanding of what we're supposed to do here, and we'll be experts at solving systems of equations, at least by graphing. We will continue to do this for the next couple days, probably tomorrow and Monday as well, just to get as much practice as possible. Good luck. Do not forget to do your CYU or your lesson question.